Hello and welcome back to Calculus2, section 6.10, Hyperbolic Functions. This will end chapter 6, and we are going to see now these new types of functions, which you guys obviously haven't seen so far. Hyperbolic functions have interesting names like Sine Hyperbolic X and Cosine Hyperbolic of X and so on. And even though they share some of the name with trig functions, these functions are nothing like trig functions. The goal of tonight is to take a look at these functions, see their definition and how we work with them, and then jump into calculus as well to find derivatives and integrals for these functions. So first half of the lecture is pre-calculus based, where we define functions, we take a look at all of the properties, and then the second part is calculus for those functions. So first of all, the idea of hyperbolic functions. One of the greatest figures in mathematics, Leonhard Euler, discovered the relationship between trigonometry and exponential functions. This is not the part of the lecture, these formulas, but they are essential to understanding how these hyperbolic functions came about. He figured out that you can take sine x and write it as e to the ix minus e to the negative ix over 2i, and cosine x is equal to e to the ix plus e to the minus ix over 2, no I in this case. So these functions were defined, sine and cosine were defined through complex values. And he was the one to discover that. And then he asked himself, well, the world of sine and cosine trigonometry is very rich. What would happen if I'm to remove i's? If I'm to remove this complex part, what would happen with the remaining part? So he goes and he says, all right, let's just remove this, and then he works out properties. He works out the properties in his head, obviously, because he was blind for most of his life. And when he figured out that all of these properties were similar to trigonometric properties, and it was also plentiful, area of rules and so on, he decided to call them hyperbolic functions. And then he said the definition for sine hyperbolic, I'm going to do that in red. Definition for sine hyperbolic is e to the x minus e to the minus x over 2. Definition for cosine hyperbolic, oops, I forgot to put x. Wow. Sine hyperbolic x, cosine hyperbolic x is e to the x plus e to the minus x over 2. So these two are definition for 2 out of 6. And then what he did is he used the same idea as in trigonometry to get the secant and all of the other ones. So from here, he says that tangent hyperbolic x is going to be sine hyperbolic x over cosine hyperbolic x, which once you cancel the 2's in division, you get e to the x minus e to the minus x over e to the x plus e to the minus x. Further, cotangent hyperbolic x is going to be 1 over tangent hyperbolic x, or cosine hyperbolic x over sine hyperbolic x, which is e to the x plus e to the minus x over e to the x minus e to the minus x. And the remaining two, secant hyperbolic x is to be 1 over cosine hyperbolic x, which means 2 over e to the x plus e to the minus x. And finally, cosecant hyperbolic x as 1 over sine hyperbolic x, which is 2 over e to the x minus e to the minus x. So these were the properties, not the properties, sorry, these were definitions of all 6 hyperbolic functions. Now, as I mentioned before, these functions might remind you of trig functions, and some of the stuff is the same, like tangent hyperbolic is sine hyperbolic over cosine hyperbolic, but these functions are nothing like trig. What's the basic property of trig functions? They all have this particular thing. What is the same for all 6 trig functions? Their nature, what are they? Anyone? When you think about sine x, cosine x, tangent x, cotangent x, secant x, and cosecant x.
Is it that they all yield circles?
No. You could spin that answer eventually into what I want to. No, that's true as well, but that's not the. So they're related to circle. So everything you guys are saying is correct. Is not what I'm looking for. All six do what?
They have an infinite domain?
Yeah, but so do polynomial and exponential function. True. What is different for trig functions that let him try and then you. Yeah. They're periodic. They repeat themselves. You have a squiggle for sine, and then another squiggle for sine, and another squiggle for sine. And it keeps repeating itself infinitely long. Then you have a squiggle for tangent, and then another one, and then another one. After every asymptote, you have the same squiggle for a tangent. All trig functions are periodic. None of these are. So this is something to be very careful about. You might want to think, oh yeah, trig functions do that, so hyperbolics do the same thing. Hell no. Trig functions are periodic in nature. We can use them to model certain phenomena. These guys are not periodic, and we use them to model different things. So if you want to talk about waves, clearly you will be using trig. But if you stretch the chord between 2 points, the chord, even though it looks like a parabola, very wide parabola, it's not parabola, it is cosine hyperbolic. That's what it is. So if you are to work for, let's say, a power company, right, to distribute electricity, and you are designing power lines as an electrical engineer, you will be dealing with a cosine hyperbolic function because you need to compute the drop for the cable. You can't stretch it because it's going to shrink and it will snap. But you can't stretch it to arbitrary length because during the summer it's going to expand and it's going to get even bigger belly, right? And then a truck might hit it, or passing person might hit it. So these calculations are very important. So certain phenomena in life are going to be modeled by these functions. Also, as you guys take differential equations later on, you will see that certain type of equations will have sines and cosines, and very similar equations, you just change one sign, solution to those equations would be these guys, hyperbolic functions. So half of the answer for those particular problems would be trig, and the other half would be hyperbolics. So they don't compete, they complement each other, right? Trig functions will model stuff that it's periodic. This model different situation. The first order of business is to take a look at basic identities. So hyperbolic functions have identities, and those identities are very similar to trig ones. They are not the same. They're very close, and it's very easy to miss a sign and put the wrong thing. So please, the best thing probably would be to study both side by side and see what is different and what's the same. So let's list those properties, basic identities. Again, whether you are memorizing these or not depends on you. Your exam question will say, prove this formula, and the formula is given. And you guys will go and you will crank whatever I show you in next 5 minutes. So you don't have to memorize these formulas, but if you know trig, and if you spend some time looking at these formulas, it will be very quick for you to sort them out and get which formula goes where. So hyperbolic identities. And the first one is, you remember how sine squared plus cosine squared was 1?
Yeah.
Well, now cosine squared hyperbolic minus sine squared hyperbolic is 1. So not the same, but close. So cosine hyperbolic squared of x minus sine hyperbolic squared of x is equal to 1. And then you remember how you had 1 plus tangent, 1 plus tangent squared was secant squared? Now it's going to be 1 minus tangent squared is secant squared. So just so it gets sufficiently annoying. Most of these signs change. And then you had you had the cotangent squared minus 1, plus 1. Now you have cotangent squared minus 1 equals cosecant. So cotangent hyperbolic squared x minus 1 is equal to cosecant hyperbolic. Oh, these are squares on the right hand side. They're all squares. Now we have the sum of the values. If you remember your sine of x plus y and cosine of x plus y, you still have that here. So it's going to be sine hyperbolic of x plus y. And this formula remains the same as the one. So this one is the same. Sine hyperbolic of the first, cosine hyperbolic of the second. And then keep the sign, which is plus. Sine hyperbolic of the second, cosine hyperbolic of the first. So this formula is identical to the trig one. But then cosine immediately, cosine hyperbolic is going to be off. Because you don't get to change the sign. So it's going to be cosine hyperbolic x, cosine hyperbolic y. That looks the same. And then you put plus. For trig, it was a minus. For cosine, you had to switch the sign. Well, in this case, the formula looks the same. It's the opposite sign in between. Now you might ask me why, which is where I say, well, just do the proof, and we'll see how that works immediately. And now this is very interesting. Cosine hyperbolic, I mean, interesting to me. I don't know, you make your own interest. Cosine hyperbolic squared, sorry, not squared, 2x. Cosine hyperbolic 2x is cosine hyperbolic squared x plus sine hyperbolic squared x. When I saw this as a student, I just wanted to explode because, come on, you have sine squared plus cosine squared is 1, and you have cosine squared minus sine squared to be actually cosine 2x. These two formulas are actually swapped with trig. If you remove ages, this result is that one, and this result goes there. If you remove ages. These two formulas, so this is why it gets to be so confusing. Another formula that stays 100% same is sine 2x. 2 sine hyperbolic x cosine hyperbolic x. And these guys are almost the same. Cosine hyperbolic squared x is equal to cosine hyperbolic 2x plus 1 over 2. This one is the same. The other one is sine is off. Hyperbolic squared x is equal to cosine hyperbolic 2x minus 1 over 2. It should be 1 minus cosine for trig. Yes, over here is plus 1. Yes? This is supposed to say sine, yeah. That's wrong. This one is wrong. Everyone, locate this first. I'm going to erase it. Locate that one. That is supposed to be sine hyperbolic y. Very good catch. Replace this with sine hyperbolic y. It goes cosine hyperbolic x, cosine hyperbolic y, plus sine hyperbolic x, sine hyperbolic y. So this needs to be sine hyperbolic y. What type of exam questions are you going to expect here? Well, prove any of these. And the proof is done by simply replacing your sines and cosines with ease. Hyperbolics, with ease. So, pick any of these formulas. Whatever. Just 1, 2, 3, 4, 5, 6, 7, 8. Just give me a number. 7. 1, 2, 3, 4, 5, 6, 7. That's the sine 2x. All right. Prove sine hyperbolic 2x is equal to 2 sine hyperbolic x cosine hyperbolic x. This formula looks identical to the trig formula. You remove ages, it's the same. Now, how we do the proof? We know that sine hyperbolic is given as e. Now we have to put 2x because the argument is 2x. Minus e to the minus 2x divided by 2. That needs to be the same, I'll put the question mark there, as 2 times, instead of sine hyperbolic x, I will write e to the x minus e to the minus x over 2 times e to the x plus e to the minus x over 2. You see that I replaced all of the sines and all of the cosine hyperbolics with their e definitions. Now, these two cancel. There's nothing that we can do on the left-hand side, so e to the 2x minus e to the minus 2x over 2 stays. And then on the right-hand side, I can FOIL. So x times e to the x is e to the 2x because it's x plus x, right? And then I have plus e to the x minus x is e to the 0, so plus 1. And then I have minus 1. and minus e to the minus 2x over 2. As soon as these two cancel, you see that the left-hand side and right-hand side are the same. So these are very structured, very easy in the sense that you don't have to, if you're good with algebra, you don't have to think too much of how to do the proof. All of these are the same. You replace your sines and cosine hyperbolics with ease and just follow algebra throughout the problem. So let's pick another one. I will give you some time to work on it, and then I will do it. Do you have another formula that you would like to try? Pick obviously what you don't like at all, because I will work it out 100%. And then
So you give it to us?
yeah.
Can we do the second one?
Second.
Minus tangent hyperbolic square root of x.
Okay. So let's go with that one. Now I want you to try on your own. So prove 1 minus tangent hyperbolic squared x is equal to secant hyperbolic squared x. Guys, if you go all the way up, right here in purple, you have definitions for tangent and secant, right? You can still work them out as sines over cosine and so on, but if you have those direct definitions, you can work on those. All right, so no pressure. You have 18 seconds.
Secant hyperbolic of x is 2 over e to x plus e to the minus x, or 1 over e to the x plus e to the minus x. Yeah. So this is 1 over 2 over. 2 over? Okay, so I did this, and I got 1 over. So
think about it. Follow the algebra.
let's take a look at this together. Again, this is one of the basic identities. Most of the people will be remembering these identities because they want to be cool, I guess. So what do? I will copy the 1 minus tangent is going to be sine, so e, hyperbolic, right? So e to the x minus e to the minus x over e to the x plus e to the minus x needs to be the same as, oh, sorry, all of that squared. Needs to be the same as this one is the coso e to the x plus e to the minus x, all of this squared. Now, if you carefully look, you see that you have the same denominator already, and they're both squared. So how about we find the common denominator, the master common denominator for the entire problem, and just don't worry about denominators at all? Well, I would have to write 1 as e to the x plus e to the minus x squared over e to the x plus e to the minus x squared minus e to the x minus e to the minus x squared e to the x plus e to the minus x squared, question mark, 4 over e to the x plus e to the minus x squared. So observe that all denominators are the same now, so I don't have to worry about those any longer. Just forget about denominators. If you multiply both sides of this equality, right, with e to the x plus e to the minus x, the entire denominator everywhere, they just go away. So we just look at the numerator. When I square the first one, I get e to the 2x plus 2 e to the x e to the minus x plus e to the minus 2x minus, we do the same thing but put in parentheses, e to the 2x minus 2e to the x e to the minus x plus e to the minus 2x needs to be 4. E to the 2x. Now this is 1 because it's e to the x minus x is e to the 0. E to the 0 is 1. 1 times 2 is 2, so plus 2. Plus e to the minus 2x minus e to the 2x plus 2 minus e to the negative 2x, and that should be 4. This and this cancel, this and this cancel, and there it is. 4 equals 4. Proved. This is the entire problem. It's 4 lines. Looks messy, but it's 4 lines, guys. You multiply both sides of the equality with that denominator. It cancels it everywhere. Would you agree? This has to be on the exam.
No, this particular problem.
Well, let's see the other ones. The ones that are worse. These are the basic ones. Let's see the actual problems. So basic skills. This is an interesting one. I'll let you work on it for a few minutes. Problem 14 in a textbook listed under basic skills. 2. Well, I'll just put prove or verify, whatever verb words you'll run into. So verify that 2 sine hyperbolic of, I can't fit there, 2 sine hyperbolic of ln of secant x is the same as sine x times tangent x. The
Hyperbolic X?
Nope. Regular. So secant, sine, and tangent are trig functions. The only hyperbolic one is the sine hyperbolic. So 2 sine hyperbolic of ln of secant x is equal to sine x times tangent x. None of those are hyperbolic. Only the first one, sine hyperbolic, is the hyperbolic one. Try it. Plug in all the e's and follow the algebra. Be right back. All done? Let's take a look. 2 times the fraction e raised to ln secant x minus e to the minus ln secant x over 2 should be equal to sine x tangent x. Well, 2 and 2 cancel. The e and ln cancel, and I just get secant x minus, now on the other one, what I have is the negative goes as the exponent of secant x and makes it into e positive ln, and then that becomes cosine x, because 1 over secant x is cosine x. Question mark, sine x, tangent x.
Explain that again. What do you do with the sign? The negative
The rule for logs is p ln x is ln x to the p. So you had negative 1 times ln secant x. So this negative 1 goes as the exponent of this one, and then it becomes ln 1 over secant x, which becomes ln of cosine. So now in the next step we have secant x minus cosine x, and that is supposed to be equal to sine x times tangent x. And now we converted the problem into a trig identity, so now you have to figure out what to do here. Now you are allowed to actually work on both sides if you want to at the same time, but as you can see, on one side you have multiplication, on the other side you have subtraction. So what should we do?
we reduce it to one term, so you make it sine squared of x over cosine x.
On the right hand side,
Yeah.
right tangent as sine over cosine. Okay, great. So secant x minus cosine x should be sine squared x over cosine x. Do you see now that you can multiply both sides by the cosine? Are we okay with that? Multiply both sides by cosine? On the right hand side, secant times cosine is 1 minus cosine squared x is equal to cosine and cosine cancel, sine squared x. Huh. Sine squared x plus cosine squared x equals to 1. 1 equals 1. Done. What an awesome problem. So just by multiplying both sides by cosine x, we deal with this thing. So those would be the identities. The next part and the last part of the pre-calculus portion are the properties of each one of these, which you obviously discover on your own. I will work, let's say, on hyperbolic cosine as the one that is most useful in application of all of these. So you can do the same thing for all other ones, right? So what I want to do is analyze cosine hyperbolic x. So cosine hyperbolic x is defined as e to the x plus e to the minus x over 2. The graph for it has no asymptotes of any kind. It looks like a parabola, but it's not a parabola. What it does is it goes through origin. You can verify that quickly here. As you put x equals 0, you get e to the 0, which is 1, plus e to the 0, which is 1. 1 plus 1 is 2. Oh, it goes through 1. It goes through 1. So you have all of those properties that you learned in pre-calculus you can apply here. What do you know? First of all, you see domain. Negative infinity, positive infinity. You see range. 1 to positive infinity. You see x-intercept, none. Y-intercept, 0, 1. This function is even because it's symmetric on the y-axis, and since it's symmetric on y-axis, we have the property which says that negative cosine hyperbolic x, cosine hyperbolic x is the same as cosine hyperbolic of negative x. So that's the property for even. No asymptotes. And so on. You can create this, should I call it a card? For each of the remaining 5 if you're interested. You would go, you will Google the graph, or you will use Mathematica, even better. Use Mathematica to graph it. And I believe that your calculators might have some of these trig functions, hyperbolic functions under catalog. So if you have your TI-8384 with you, let me just check. So catalog is yellow 0. And then I want invert cosine hyperbolic, so alpha c. Okay. Second catalog. Oh, alpha is already there. So where is C? Go. There it is. You have a cosine and cosine hyperbolic. So if you list through C's on your calculator, you will see. Now, obviously, you guys have this form. If I ask you to compute cosine hyperbolic of 7, you will put 7 over here, 7 over there, punch everything in the calculator and get the number, right? Or you can use the catalog and then use that as, I could bring the arrow cosine hyperbolic and you put 0, let's say it should return 1. Does it matter radians or degrees for this calculation? And the answer is no. Radian and degree only are important for your trig calculation. You're not dealing with angles. These are not periodic functions. They have nothing to do with angles. So what you do is you either compute here using calculator or use here using calculator in a different way. So you can compute those. So you can go and you can now repeat the same procedure, find the graph for hyperbolic sine and cosine, all of the other, tangent, cotangent, and all the other ones, one by one. We also have inverse hyperbolic functions, and if those show, again, a whole bunch of formulas for inverse. And their definition are in the textbook, you might run into, depending on who's teaching differential equations and so on, you might run into, you know, one of these. But these are their definitions. It should be common sense that they are ln's, because the definition of the main right function is in terms of ease. Its inverse better be defined in terms of ln, because ln is the inverse of e. So that should be common sense and expected to have ln for all of them. And then these are very interesting, right? That they work out that way. Can you prove that this is inverse? Sure. Do function composition. Right? Take this ln of the, right? And plug into each one of the x's for ease, right? From sine. And when you calculate, at the end you're going to get x. And that proves that these formulas are inverses of hyperbolic functions. Now, they also in the textbook, if you're interested, again, this is not honors course, so you don't have to worry about it. But let's say you want to worry about it, you can take a look at how to derive one of these. I'm not sure which one they did, inverse sine or inverse cosine. They did hyperbolic. They did one or the other. You can look it up in a book and then try another one if you're interested in learning how it's done. It's just the standard stuff. You interchange x and the y, which is the way to find inverse function, and then follow algebra from there. I don't think that any of you should have issue with that, following that algebra, and then right, try one of these on your own. So the last part, right, which is the second part of this lecture, is calculus of hyperbolic functions. Are those cakes? Looks like a route. All right. What do we have? Hey, we have derivatives and integrals. Did you memorize your trig ones? Perfect, because these are the same, except the minus signs are on different spots. They are the same, and you need to know them. If I ask you to prove the identity, I clearly placed the identity on the exam. But if I ask for the tangent line, if you don't know what the derivative of tangent hyperbolic is, clearly you cannot do that problem. So we start by memorizing derivatives. The derivative of sine hyperbolic x is cosine hyperbolic x. Ooh. Right? The derivative of cosine hyperbolic x is sine hyperbolic x. Observe there's no negative there. You had negative for trig. The derivative of tangent hyperbolic x is going to be secant hyperbolic squared x. Same stuff as before. What else do we have? We have what else? I don't think they actually listed these in the book anywhere. At least I can't find them. Yeah. You have derivative of cotangent hyperbolic x, which is going to be negative secant hyperbolic, no, negative cosecant hyperbolic squared x. You have the derivative of secant hyperbolic x, which is going to be negative secant hyperbolic x tangent hyperbolic x, and the last one cosecant hyperbolic x is equal to, again, negative cosecant hyperbolic x cotangent hyperbolic x. So signs are off. You don't have this change of sign in this derivative. You should. And you have the extra minus sign creeping up in here. Well, yeah, these guys, I'm not changing anything. So these guys over here all have pluses, and the ones underneath, they have minuses. Yes? Well, this is the next question that you will be dealing with. No. Just take the derivative. And you have the derivative of, let's go with sine hyperbolic of 3x. So how do you take this derivative? What's the derivative of sine hyperbolic? Cosine hyperbolic of 3x times 3 in chain rule. Nothing special, guys. Nothing special. I want to take a look at a few formulas from, also a few problems from the textbook. So let's do 3 or 4 of these guys. The first one is number 24. They want you to compute the derivative for y equals negative sine hyperbolic cubed of 4x. That's your first assignment. Find the derivative. So you will start in a new line. You will write d dx of negative sine hyperbolic cubed 4x. Right, that belongs to hyperbolic as an argument. All right, let's see. Take the derivative. Be mindful of the chain rule. we have to use chain rule, right? So we first deal with the cube. So this is going to be equal to -3 sine hyperbolic squared of 4x. And then the derivative of sine hyperbolic is cosine hyperbolic 4x. And then finally times 4. So we have two chains in this case. So the sine goes into cosine hyperbolic and then 4. So two chains. That minus in front really did nothing. So this is -12 sine hyperbolic squared 4x times cosine hyperbolic 4x. Let's take a look at another problem. Sure.
I know this is a top one question, but -3 and then it's h squared, right? Because we just like bring down the
Exponent, yes.
yeah, and then 4.
So exponent goes down. Now this would be the same as, you know, x cubed. It's 3x squared. So there's your 3x squared. You're welcome. We'll do another one. Well, let's do 26 and 28. So 26 says find the derivative of square root of cotangent hyperbolic 3x. So the square root is the 1/2 exponent, right? We start from there. So 1/2 of cotangent hyperbolic 3x raised to the -1/2 times the derivative of the inside. The derivative of the cotangent is cosecant. Yes, cosecant hyperbolic squared. Very good. Cosecant hyperbolic squared of 3x, and then we still have times 3. But we have to be careful, there is a negative as well. The derivative of cotangent is a negative cosecant squared. So there's a negative there. So now when you put all of this stuff together, we have -3 cosecant squared hyperbolic 3x divided by 2 times square root of cotangent hyperbolic 3x. Bueno? Nice. All right, one more derivative, and then we show the integral real quick. So the derivative of x tangent hyperbolic x. What should we do? What should we do here? Yeah, but what do we have? Multiplication. Okay, so what do we use? Product rule. You see, there is, guys, look. Function number 1, function number 2. It's the product rule. Copy the first times derivative of the second plus copy the second times derivative of the first, which is just 1. So if we don't write that one, that's it. We're done. So be mindful of the, product rule, quotient rule. Quotient rule is number 30. They ask you to do x over cosecant hyperbolic x. I'm not going to do it. I'm just going to work some magic here. So how's your quotient rule? Yeah, exactly. You don't need to know it anymore. Change it into a product. Exactly. Cosecant hyperbolic is going to be sine hyperbolic on top, right? All right. You can always cheat on those. Integration. Use U sub. Use U sub. And I'm done. Right? Integral of sine hyperbolic 5x dx. You would change the 5x with u. So the answer is cosine hyperbolic 5x over 5 plus c. You know that the sine x, the integral of sine x is negative cosine x. The integral of sine hyperbolic x is positive cosine hyperbolic x. So you have to be careful. They are close, but they're not the same. And that minus is one of the things that is making a lot of noise. So you have to use U sub if you can't solve the problem in any other way. Or you have to use identity of some sort. Let's take a look at problem 33. This is the textbook example. Integral sine hyperbolic x over 1 plus cosine hyperbolic x dx. U equals 1 plus cosine hyperbolic x. du is sine hyperbolic x dx. It's exactly what you have here. So the problem quickly becomes du over u, which is ln u plus c. Which is ln, or the absolute, 1 plus cosine hyperbolic x plus c. And that's problem 33. It's extremely quick if you know u sub, which is what I told you to practice a lot for this course. How about 32? Integral of secant hyperbolic squared x tangent hyperbolic x dx. In order to do successful u substitution, you should locate function derivative pair. What is the derivative of what over here? So secant squared is the derivative of tangent. So whatever is the function, that's your u. We go u equals tangent hyperbolic x, du equals secant hyperbolic squared x dx. So this and this is du, and then the rest is just, right? So it's u squared over 2 plus c, which is 1/2 tangent hyperbolic x squared, or you can put the square here, so you don't have to deal with parentheses, plus c. So guys, 100% of these integrals are u sub. If you are not comfortable with u sub, it's not going to be pretty. I understand we are over time already, 2 minutes, Do you want one more integration problem and then break? Let's do one more by popular demand. And this one is going to have limits because we haven't done anything like that. So 39 says integral of tangent hyperbolic x dx from 0 to ln 2. So we'll take another 2-3 minutes to solve this and disappear into the night. How are we going to integrate tangent hyperbolic? Is it on the list of basic integrals? No. So you have to rewrite it as, this is tangent. Sine over cosine, yes. So you will rewrite this as 0 to ln 2 sine hyperbolic x over cosine hyperbolic x dx. And then, again, u sub, always u sub, u equals cosine hyperbolic x, du equal sine hyperbolic x dx. We have integral of du over u. Note that I'm not putting limits because we have to go back into original variables. So we get cosine hyperbolic x over here, and the limits are 0 to ln 2. Now we need to compute this monstrosity and we're done. So we have ln of, and now cosine is e to the ln 2 plus e to the minus ln 2 over 2 minus ln of cosine hyperbolic of 0. Now you know that's 1 already because we did that before. I have ln of 2 plus 1/2 over 2 minus ln of 1, which is 0. So what I have here is ln of 1 plus 1/4, and the answer is ln 5/4, whatever that works out to be. Remember the trick that this negative goes as the exponent, so 2 to the negative 1 becomes 1/2. E cancels ln, and that's your 1/2. And then 2 divided by 2 is 1. Half divided by 2 is 1/4. Keep the plus. 4/4 plus 1/4 is 5/4. And you walk away. So the half, this is the same calculation we had earlier. When you have a negative in front, it goes as the exponent. So 2 to the minus 1 becomes 1/2. So you have e to the ln 1/2. E and ln cancel, you just have 1/2. 2 divided by 2 is 1, 1/2 divided by 2 is 1/4, 1 plus 1/4 is 4/5, 5/4. And that's the end of it. All right, that's it for tonight. Oops. This is the one.